like CNRS, Government Research
Oh,
Lab.
Government Research Lab, I see, that's what you were saying. Okay,
Yeah.
I didn't understand that. It's not quite a competing organization, but it's associated organization or something.
Oh,
No, it's competing organization, okay. It's the place you were at.
Yeah.
Yes, okay, competing organization, it wasn't at Monash, sorry. I mean, I got this off the website of Monash, but that's not when he did the work. Yeah, I didn't know that. He did the work before. Okay, so these are the prettiest pictures there are. And what are these things? Well, this is the cylinder, this blue thing. And then this is a perspective plot here of some surfaces of, oh, and I should know this, their vorticity probably in the Z direction, I think. Okay, of course what you see is the shadow, the skeleton, that's the original 2D wake. This structure here, or here, 1, 2, that's the original the original von Karman vortex wake, the one that you saw that the mountains were doing, or that picture with the Taneda experiment, and that's this. Right? Remember, we were talking about a 2D flow, and what were those two dimensions? They were X, and in this picture, it's Y. This is the Z direction, which we originally had over here, and it was a direction in which nothing was happening. The cylinder was infinite, and here it is here, and here it is here. So the original wake just had structure here, here, here. It did not have any structure as far as the Z direction. These blue, yellow things, that's the instability. That's the new instability, the 3D instability. This is the 3D of the the D of the 3D. Okay? And, okay, so do people get this really? Because I know, I should say, the hardest thing about 3D flows is showing their pictures of them, and to someone who has gotten used to them, it's so obvious what you're looking at, and someone who is not so used to them, they don't know which direction is which. So I'm in the position, I can't ask you because you're also in that position, of definitely knowing what all those dimensions are. Only you can say if you don't know what this picture shows. Only you know that. So do you know what that picture shows? Do you see that this is the infinite cylinder that before was over here? And before this instability, there was no variation in this direction, but there was variation. There was this period, there was this kind of, there were those things that did this, and that's them here. I think this picture is really good in orienting one. Okay, so that's this column. What's this column? What's this column? This column is a different instability. These same researchers, Barclay and Henderson, they found, you see the beta here, it goes up to 2.5. Over here it goes up to 15. So this is kind of a shrunk scale. All these things that are shown here are over here, but they found that for a higher Reynolds number of 259, there was another instability here at a higher beta. Higher beta is a wave number. Higher beta means a smaller period, smaller wavelength here. So in fact, I think maybe I had that wrong. No, I had that right, that's right. Higher wave number is smaller wavelength, and that's what the small wavelength is. All these wavelengths are reported in units of the diameter. So this thing here, from yellow to yellow, is about the diameter. Whereas here, from yellow to yellow, is about 4 times this diameter. So this is the bifurcation that first appears, and this is a bifurcation that appears second. And we didn't get to it before, so we didn't have time. Yeah, let me do this. The last class, there was a part I left out, which I didn't mind leaving out. We had plenty to say. But I'll just have maybe you remember that we skipped it. We said, suppose we had bifurcations to 2 wave numbers, here called M and N. What are the possibilities of what happens here? And we did the same thing, equivariant, blah, 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 blah. We've done this so much, it got very boring, and we end up with states that could be M, states that could be N, the 2 different wave numbers, and states that could be a combination, just the same way we did traveling waves to the right, traveling waves to the left, or standing waves that were a combination. But here it's different, because when we did traveling waves, the right going ones and the left going ones are equivalent. Whereas here, when we have two different wave numbers, that's different. Being 4 times the size of the diameter is not the same as being 1 time the size of the diameter. Those are different things. So that meant that the equations were different, the pictures were different, so we ended up, I mean, we didn't do this, but we ended up with having bifurcations and then other branches called mixed modes. And they could occur in different ways, just as we did in the, okay. So we have an example of that here, which is coming back and is here. Okay, so here we are. So here are some more features of this bifurcation, all coming into what we've been discussing. The first bifurcation, the one that to the what's called the A mode, with the wavelength of 4, it turns out to be subcritical. Okay, and so here's a couple things about that. I think we discussed this. Subcriticality means that you have 2 different thresholds. One, as you go up, you jump up, and as you come down, you go lower than the place where you jumped up. And it's got to be a 5th order equation to describe it, because otherwise you couldn't. You can see that this solution to a cubic equation is going to look like this. If you look at, this is how we draw bifurcation diagrams, but we know that we're turning this around, and we get a solution to a cubic equation with the 0 guarantee. Right? Okay. To get an equation, to get something that does that, okay, so this is 3rd order. This has to be 5th order. To get this many, you can see how many minima you have here. You have 2 extra ones. You need 2 more orders to get those there. So there's 5th order, and so if you were to calculate a normal form that fit all this, you would need 5th order terms. Okay, so that's one thing. And one way that you can check for that is you can see if you're, the linear, what's called linear growth, again, this I find very confusing. It's called linear growth, and I emphasize what makes something a linear equation. I said this some time back. When's the most recent time I said this? I said the epsilon appears 1 time here. Okay, we call this linear growth sometimes, even though what it is exponential. It's because epsilon dot is a linear function of epsilon. There's only one function which is proportional to its derivative, and that's the exponential. Right? So linear and exponential are sometimes kind of mixed up. Just as, sometimes when people say in popular press, they say, oh, it grows exponentially, and by which they mean it's big, but of course, it all depends on the lambda. Exponential growth is also very small in the beginning. It's proportional to its value. Quadratic growth is faster if you have a small, if you're in the initial stages. And so too, people don't take into account that exponential decay is also very rapid. Anyway, so coming back here, the first term that is not the linear growth, i.e. the exponential growth, comes in at the 3rd order term. That is to say, what is the behavior of this? It's mu a, okay, until a gets bigger, in which case this term starts to be important, and finally this term gets to be important. So if this term had a negative value, minus, that would be supercritical. Oh, that doesn't help. A supercritical bifurcation would be, this would have a negative sign, and this wouldn't be here. And you would find that when you were going in time, that when you stopped having the exponential growth that comes from the mu, you would exit it to the right and saturate there. Your curve would look like that. But that's not what happens. Because this term is positive, when you stop having a simple exponential, you go up, and it's only when the 5th order term comes in that you saturate. And this is important for experimentalists or numericists because this is blown up here. But if I hadn't drawn this little teeny dash, it takes forever to get to points that are near thresholds. It takes forever because the time scales are all very slow. You have lambda very near 0. You can be hanging out here forever, and it looks as though it's stable, but it's not. Or it looks as if it's going to grow, but it's not. and it takes you forever to get points like this, and you can see that if without these little things to guide your eyes, you wouldn't really be that sure that it didn't just, it really depended a lot on this point here, this one point. This is a much more robust method for deciding whether you're sub or supercritical. When you leave the exponential growth, do you leave it higher or do you leave it lower? And you can see that over here, that's not the case. Over here, you're leaving it, and you're leaving it lower. This is the original exponential growth, and you're leaving it lower, and that tells you that the sign in front of the cubic term is negative. This second bifurcation is supercritical. The first one is subcritical, the first one is supercritical. It's very, very slightly subcritical, but it is subcritical. Okay, so that's one thing you can see. And then the second thing that you might see is the presence of mixed modes, which, as I said, are the things that we skipped last time, where you have, which are like the standing waves, where you have both present, not just the A mode or the B mode, but a combination. And that combination is seen here. That is to say, the whole bifurcation line diagram looks like this. You start off with the 2D solution. You have this slightly subcritical bifurcation to the A mode. The A mode is the one that had the lambda that's 4, that looks like this. You have a slightly subcritical bifurcation to that. There's also another bifurcation to the other one, which is supercritical, the one called B, called mode B. They were called mode A and B a long time before they were actually studied numerically. And then there exists a mixed mode. This A undergoes a bifurcation to create a state that's a combination of A plus B, and then it goes into the B there. And that's one of the several possibilities that can happen. It's like with the standing waves and traveling waves, you recall that there were several possibilities, and here too there are several possibilities. But this is the one that happens. And this finally explains this picture from long ago. This is just a regular bicarbonate vortex. This is mode A here. This is mode B. And then there's a tiny period of, okay, first of all, there's a tiny bit, it could be hysteresis, and it turns out it is over here. Right, there's a gap, and there's a place where there's both solutions. And over here, there's a place where there's both mode B frequency and mode A frequency, both. And that is not representative of hysteresis. That is representative of a spectrum that contains both. A mixed mode where you have both A and B. That's one of those modes that you look for solutions to these equations. You know that you could look for equations, we did it last time, that have just A. You can look for equations that have just B. But you can also look for equations that have both A and B, a mixed mode. And depending on the signs of the alpha A's and the beta and all those nonlinear, there exist such things or there don't, or there exist such things or they don't exist. There aren't. And they are stable or they're not, depending on the signs of these nonlinear coefficients. And that is, but it turns out that it's that way. Where there's A, then there's a mixed mode A plus B, and then there's B, and that's the end. And let me ask you then some questions. First of all, there's homework that's associated with this, which I didn't have printed out, but which I will have printed out so you can practice on it. Then, as you have heard, to get through the class the way I usually practice it, I would need more time, and so I've added more sessions on Wednesday and Thursday afternoons. Each of the class, after the first class or so, the classes are fairly independent of one another. So it doesn't matter so much whether you, the first one I think is definitely basic, but after that you can kind of pick and choose. And I have a number of topics, and I think I would like you to tell me which topics you want to cover. I have one that on the Hamiltonian systems, which is not that related to all the rest, but somebody here was telling me he was interested in Hamiltonian systems. That was you. Okay, so I was thinking, I mean, nobody else told me they were interested in something, so I thought I'd do my class on Hamiltonian systems. There was talk that I should add something that doesn't usually go in this class, something about computational methods. And there seemed to be some interest in that, so I thought I'd do that. And then a third thing about transition, kind of modern approaches to transition. So those are, let's see, how many classes are left? Wednesday, 1, 2, 3, 4, 5 classes left. So Hamiltonian systems, transition, computational methods. That means I have 2 more of my usual classes left. Let me tell you what they are, and then you can choose between them. Let's see if I can do this. Yes, okay, so here they are. I think I'm almost sure to skip quasi-periodicity. It's not very related to fluids at all. What did I say? I'm picking 2? Is that what we said? Yeah, 2 more. Oh, well, that's easy. Then there's these 2, stripes and patterns and reaction diffusion. Okay. So let's see, if I did that, just counting, okay, I could do this tomorrow. That would be Wednesday morning. Then, no, wait. I have not counted this right. Oh, Wednesday, Thursday. Okay, Hamiltonian systems, computation, transition. No, that does work out. Right, okay, so I can do stripes and patterns, and I can do reaction diffusion. Yeah, okay, I can do all that. Okay. Okay, but then the question is the order, perhaps. Different people perhaps cannot be here at different times and would prefer different times. Can you, anybody who has any thoughts on that, can you tell me?
In the regular classes, can we have the stripe patterns and reaction diffusion equations?
Oh, that we'd already decided. That
That's
was
the
already
regular.
decided, yes, okay. Should that just be tomorrow? Just those 2? Or, I mean, you Hamiltonian person, can you make it any time?
It's okay for me.
Any time is okay for you,
Yeah.
so that could, okay. And people want to see computation or transition. Which times should those be? Morning? Mornings.
Usual time transition.
Okay, transition and computation should be in the morning.
So
Okay, sorry?
So I can't be here Friday morning.
Okay, so not for, okay, and
No.
you, but you're kind of interested in those topics?
Well, more the
More,
transition.
sorry, more transition one. Okay, right, okay, so transition on Thursday morning. Oh, no, okay, so that's easy.
Yes.
So tomorrow goes stripes and reaction diffusion.
Yep.
The next day goes transition in the morning.
Yep.
The next
Okay.
day, and then Hamiltonian in the afternoon, and then computation on Friday.
Yep,
Does
makes
that-
sense.
No?
You mean Hamiltonian in Friday afternoon?
No, Thursday afternoon. Did I count that
Yeah,
wrong?
it's okay. Thursday is okay.
Did I say that right? Okay, let me write it down. So, Wednesday morning would be the stripes. Wednesday afternoon is reaction diffusion. Thursday morning, Thursday afternoon, okay, Friday morning is transition. And you Hamiltonian person, would,
Thursday afternoon.
you want Thursday afternoon for Hamiltonian,
Yeah, 7.
right, and computation was Thursday morning. Is that what we said? No.
Transition.
Transition, Thursday morning. Yes. Oh, right, that's the day you couldn't make. Right. Okay, so the transition and computation. No.
Can we switch
Sure.
reaction diffusion somewhere, because Wednesday afternoon is clashing with another course in Uni Melbourne.
Okay, fine. So
Like,
which one are you not interested in then?
I am not interested in Hamiltonian and computational one.
Okay, hold on. So can Hamiltonian be here? Is this okay?
Which day?
On Wednesday afternoon?
Sorry.
No.
I have a seminar. You
No, that's not, okay, hold on, not a problem. Okay,
Wednesday,
hold on.
Thursday, both afternoons is clashing for us.
Both
Like, we
after-
have a course in Uni Melbourne.
Yeah.
Okay, hold on. Okay, but I'm sorry, so what would you like, what would you like not to see? Or, I mean, what would you not be
Yeah,
most
I'm not
indifferent to?
interested in Hamiltonian and computation levels.
Okay, you're not interested in computation, okay, but computation, it has to be, oh no, it doesn't necessarily have to be there. Hugh, oh, no, but that's the one you're not interested in, is computation, right, okay. So, hold on, we'll leave that as it is for the moment. So you may have to miss one of them. You're not interested in Hamiltonian, you say, but you have the same class schedule, you two, or
Well-
what's okay for you?
Oh, Thursday is okay.
Thursday's okay,
The whole day
anytime.
is okay for me. Thursday.
Okay, but Thursday afternoon you don't have a class, so it doesn't matter for you, so it's not,
Yeah, Thursday afternoon is my class.
it's your class, okay, so good, so I put in Hamiltonian,
Yeah.
and that solves one of the problems, right, okay. Okay, so stripes, and then what are we trying to put in?
Reaction diffusion. Maybe
Reaction
Thursday morning.
diffusion is Thursday morning, okay.
Friday afternoon.
Or
No,
do we
there is
have
no
a slot
Friday
on
afternoon.
Oh, we don't have.
No,
No.
and then, Wednesday, what's left here was transition.
Transition, I think we all are interested in.
You're all interested in, yes, okay, okay, and what's the best, okay, but you have the class on Wednesday
The
afternoon.
one in Melbourne,
Yeah.
the one in Melbourne, they'll be also recorded by my colleague. So I don't think you're in the system yet. Are you in the system in the LMS in Melbourne Uni? For that subject, the one with Gary Brown.
Yeah.
Are you in the system? So
I don't know LMS, I am in the
So,
audit list.
okay, good. So right now, we already have the video uploaded even from last week. So all lectures here at Melbourne Uni are all recorded by me and my colleague. So, so if you attend one of them,
Mhm.
yeah, you can't have both ways.
Okay.
Unfortunately, so yeah.
But still, I mean, yes, I agree, but I would still like to maximize the possibility,
Which
so.
one is more important to you? Reaction, diffusion, or transition?
Actually both.
Okay, so if we put transition here, and then you still have to miss something, you still have to miss the stripes, though, right? But hold on, right, the yeah, I guess, that, so which one, you would miss stripes and Hamiltonian, right?
Myself?
Right, you.
I would miss Hamiltonian and computational.
So you
No, I'm sorry, I don't mean what you want. I mean what you would miss with the current schedule is stripes and Hamiltonian, yes?
Thursday.
Yeah, only the stripes part I will be
This you
clashing,
that
but
would
it's
you,
fine.
mhm.
Yeah, this is one.
It's fine, there is just one clash.
Yeah, no, I understand, but let me see. Okay, and Hugh, is there something that you are least interested in?
Hamiltonian systems.
I think Hamiltonian is quite well placed then.
Yeah, okay, so, okay, so we see one conflict, which is to say that you are missing the stripes.
Yep.
Are there several people who? No, but only one conflict, am I right? Or, I mean, don't hesitate to speak out, you have as much right to an opinion as everybody else.
What time in the afternoon session?
2 to 5.
And one of them was here, wasn't it? And the other one was going to be in the other building.
Ah, okay.
Oh, is it? I need
Yeah,
to know
one
that.
of them had to be in New Horizons.
Where's the location?
The ground floor at the end, G30.
Let me write all that
I'm
down.
going to go back and check what day it was set to be. Here we go. March 15, which is Thursday afternoon. That's in New Horizons because somebody's using this, I think, for a seminar already on that date.
Did you say ground floor?
Yeah. You know the New Horizons building?
No.
That one next to the car park looks like an Xbox. That's the New Horizons building. So, and there's a coffee shop on the ground floor there. It's near that. It's just to the east of that.
So we have another seminar in Friday.
Yeah. So Laurette's class
Yeah.
on Thursday afternoon
So
will
the-
be in New Horizons.
Thursday afternoon.
Because there's a seminar or something for this room already.
Okay.
Long ago.
That's great.
Okay,
Yeah.
New Horizons on Thursday, okay. Now, are you indifferent, I'm trying to think, between stripes and reaction diffusion, which? Excuse me. No, okay, they're both, I was gonna give a
So,
recommendation, but I don't really.
I'll ask Kingo or somebody to email that out.
Is there a particular recommendation you have? I mean, I don't know the details of the contents of the.
Yes, I know, that's what I was trying to think, is
That
whether.
might change if I
That's
understand.
what I was trying to think, whether I would have a recommendation.
Like what exactly are we going to do in stripes, patterns and instability?
Yes. Stripes has to do with the the instability of stripes. Reaction, which is more. Which is more. Well, maybe, I should say, I can think about maybe. Okay, the stripes is a lot like the symmetry class.
Okay.
You can see there's pictures from the symmetry class that are right here. It's the reaction diffusion is a different sort of thing.